Welcome to lesson 7 in power system analysis. In this lesson, we will talk about transmission line modeling. In this, first we will talk about distributed versus lumped parameter models. Then we will talk about short line model, medium line model and long line model. We will also discuss voltage regulation for transmission lines. Well, as we have seen in our previous lessons, when we discussed the calculation for transmission line parameters, we found that transmission line have in general 3 parameters: the line resistance, the line inductance and a capacitance of the line to the neutral or ground. Now, as we had seen in the previous lesson, these parameters are distributed all along the line. That is, if we see a line, it will be something like this, where I have taken a small section of a line. For this line of a length delta x, we have the transmission line impedance or the series impedance of the transmission line, which is given by Z into delta x. It consists of the resistance of the line and the inductance of the line. These will be per unit length or per meter multiplied by delta x will give us the value of series impedance Z delta x for the delta x length of the line. Similarly, we will have a capacitance to ground for the line, which will be y, and for delta x of the line, this shunt admittance is going to be y into delta x. That is, capacitance will provide us an admittance j omega c, which will be equal to y, and for that will be per unit length of the line, multiplying it by delta x, the length of the line, we get y delta x. Here I had also shown conductance path for the line. Normally for 60 hertz line or 50 hertz line, the power frequency line, this conductance is negligible, and most of the time we neglect this conductance. So, we have resistance and inductance per unit length of the line. This will form the series impedance per unit length of the line, and we have the capacitance per unit length of the line, which forms the shunt admittance of the line. Now, when we talk about modeling of transmission lines, what we have to see is, if we use this distributed parameter model of the line, then the modeling of the transmission line becomes very complex, and it will result into differential equations. What we will see is that for sinusoidal voltage and current waves on overhead line, the wavelength of the line is given by this lambda. Wavelength of the line is given by c by f, where c is the velocity of light or the velocity of propagation of the waves, current or voltage waves on the transmission line. For over a transmission line, this will be very nearly equal to the velocity of light. Therefore, wavelength lambda is equal to c by f, where c is 3 into 10 to the power 8 meters per second. If we substitute this value of c, and for frequency of 50 hertz, we get lambda is equal to 6000 kilometers. That is, the wavelength of a transmission line at 50 hertz is of the order of 6000 kilometers. Since most of the transmission lines that we have are only of a few 100 kilometer length, therefore, in most of the cases we can neglect the distributed parameter model of the line. That is, the distributed effect can be neglected, and it is sufficient to model the line as a lumped parameter model. That is, if line length is less than about 250 kilometers, then one can neglect the distributed effect of the line parameters, and it is sufficient to consider lumped parameter model for transmission lines. Now, once we have used a lumped parameter model for the transmission line, then we can consider this transmission line as a simple two port network, where we have an input port where we have the voltage V s and I s, that is the sending end port. V s is the sending end voltage, I s is the receiving sending end current, and V r is the receiving end voltage and I r is the receiving end current. So, transmission line can be visualized as a two port network. For this two port network, we can write down the relationship between the sending end voltage and current in terms of receiving end voltage and current, as V s is equal to A times V r plus B times I r volts, and I s, the sending end current, is equal to C times V r, the receiving end voltage, plus D times I r, the receiving end current. Of course, the unit will be amperes. Now, this is a general relationship for two port network. It is valid for any two passive bilateral linear two port network, and one of the properties of this from network theory, we get one of the properties for this network as A d minus B c is equal to 1. That is, if we are putting this relationship in a matrix form, we get V s I s is equal to A b c d into V r I r. This is the general transmission line ABCD parameter model for any transmission line, with the relationship that A d minus B c is equal to 1. Now, transmission lines which are less than 80 kilometers long or about 50 miles long, we neglect the effect of capacitance, because the capacitive effect or the charging current is not very large and its effect can be neglected. Also, these lines are generally medium voltage and low voltage lines, because these are very short lines, and therefore, also the charging current, because the voltage being small, will also be much smaller. So, generally for line lengths less than 80 kilometer, which are generally medium voltage or low voltage lines, sometimes even high voltage lines can be there, the capacitance for these lines can be neglected. In that case, the lumped parameter model for the transmission line will consist of only the resistance and inductance, that is the series impedance of the line, the series resistance of the line and the series inductance of the line. Here the series impedance of the line Z is equal to Z into L, small z into L, where small z is the per unit length series impedance, that is R plus j omega L per unit length, that is resistance per unit length and inductance per unit length, as we have seen we can calculate it for any line. So, Z is equal to Z into L, this is equal to R plus j omega L into into L, where R is the resistance per unit length of the line and j omega L is the reactance per unit length of the line. So, from this model we have V s the sending end voltage, I s the sending end current, only series impedance Z is here R and this j omega L or X L, and I r is the receiving end current and V r is the receiving end voltage. From this circuit it is very clear I s and I r will be equal. Therefore, we can write down the circuit equation for this transmission line model as V s is equal to V r plus Z into I r. V s is going to be equal to this voltage plus the drop in this transmission line impedance, series impedance of the transmission line. This will be equal to Z into I r. So, we have V s is equal to V r plus Z into I r, and as we have already seen, I s will be equal to I r. Therefore, writing it in terms of matrix equation for ABCD parameters, we have V s I s is equal to V r plus Z into I r, and I s is equal to 0 V r into 1 into plus 1 into I r. That is ABCD parameters from here, if we see are A is equal to D is equal to 1 per unit, and B is equal to Z ohms, and C is equal to 0 Siemens. That is the unit of A and D is basically dimensionless, it will be in terms of per unit, whereas the unit of B is the unit of impedance or ohms, and unit of C is the unit of admittance or Siemens. So, from this relationship for a short line, we have A and D is equal to 1, B is equal to Z, and C is equal to 0. The phasor diagram for short line can be developed. We can start with the voltage at the receiving end at full load. So, V r F L as the reference voltage, and we have a current I r at full load, which is in this direction, that is lagging the voltage by some angle theta. Now, with this we can find out using the circuit model the voltage at the sending end, which will be equal to V r F L plus R into I r F L, that is resistance, the drop in the resistance due to the current receiving end current at full load, plus the drop in the reactance, that is J x into I r F L. So, the drop in the reactance. So, when these drops are added, we get the voltage V s. That is what we see is for lagging power factor load, where I r F L is lagging V r F L by an angle theta, we get V s, which will generally be larger than V r. That is, there is going to be a positive drop of voltage for this system. Similarly, if the current is of leading power factor, that is again choosing V r full load as a reference voltage, and since the current I r full load is a leading power factor load. So, it leads this voltage by some angle theta. Then again by adding the voltage drops, we will get R times I r F L, this is the drop in the resistance, plus J x times I r F L, which is the drop in the reactance or the inductive reactance. This will give us the value V s, and this V s, as we see, will be many times smaller than V r. That is, in case of leading power factor load, the sending end voltage magnitude can be lower than the receiving end voltage magnitude. Of course, in case of short lines, the V s is also equal to V r at no load, because if there is no current flowing in this, if there is no current flowing in this, then the voltage V r and V s will be equal. So, V r at no load is equal to V s. That is what we have shown here, that is V s is equal to V r at no load, V r and L. Okay. This we require for calculating regulation, as we will see later. Now, for line lengths or lines having a length between 80 to 250 kilometers, we call these lines as medium length lines. These lines are generally high voltage or extra high voltage lines, and for these lines we cannot neglect the shunt capacitance or the capaciting admittance of the line. The shunt admittance needs to be taken care of. What we do here is, again we are using a lumped parameter model, where the complete series impedance, that is total resistance of the line, is lumped as one resistance, and the total inductance of the line is again lumped together. So, we get this R plus j omega L as the series impedance of the line. So, Z, the total series impedance, is equal to Z into L, where small z is the series impedance of the line per unit length. Now, the total shunt admittance of the line will be y, which will be equal to small y, the shunt admittance of the line per unit length, into L. Now, what we do is, normally we divide this total shunt admittance into two parts and put them at the two ends. So, we have shunt admittance y by 2 put at the sending end and another y by 2 put at the receiving end. So, this model looks like a pi model, pi, and therefore, we call this model as a nominal pi circuit for medium length line. Now, again here we have this as a 2-port network with VSIS, the sending end voltage and current, and VRIR, the receiving end voltage and current, and we can use the ABCD parameter model for this as Vs from here we can see is equal to Vr plus Z into IR plus Vr into Y by 2. Now, if you look at this circuit, what we are finding is Vs, this voltage will be equal to the drop in this. Now, what will be the drop in this? This drop will be equal to how much current is flowing in this part? IR plus VR into Y by 2. So, IR plus VR into Y by 2 is the current. This multiplied by Z will give us the drop in this. So, that is what we are writing. VR is the receiving end voltage plus the drop. Drop is Z into IR plus VRY by 2. So, this is the current which is flowing in the charging admittance of the line placed at the receiving end. So, Vs is equal to Vr plus Z into IR plus Vry by 2. If we rearrange this by combining all the terms of Vr together, we get this as 1 plus Yz by 2 into Vr plus Z into IR. Similarly, we can write down the relationship for the sending end current. Now, sending end current Is is going to be equal to this IR plus the current here, that is Vr into Y by 2 plus the current here, which is Vs into Y by 2. So, we are writing Is is equal to IR plus Vr into Y by 2 plus Vs into Y by 2. Now, again rearranging this by combining terms, we write this as IR plus Vr into Y by 2 plus Vs. We are writing the relationship for Vs from the previous equation. Here Vs is equal to 1 plus Yz by 2 into Vr plus Zir. So, substituting this value for Vs, we are putting it here. So, V s into y by 2 we write here. So, this is 1 plus y z by 2 V r plus z I r for V s into y by 2. Now, again rearranging it, we will get this as y into 1 plus y z by 4 into V r plus 1 plus y z by 2 into I r. This is the relationship for the current I s in terms of V r and I r. So, now using these relationships we can write down this in terms of ABCD parameters as V s is equal to 1 plus y z by 2 V r plus z I r. I s is equal to 1 y into 1 plus y z by 4 V r plus 1 plus y z by 2 I r, which shows that A is equal to D, that is A is equal to D is equal to 1 plus y z by 2. This will be in per unit. B will be equal to z ohms and C will be equal to y into 1 plus y z by 4 Siemens. So, for a medium length line, when we are using a nominal pi equivalent for this medium length line, we have the ABCD parameters given as A is equal to D is equal to 1 plus y z by 2, B is equal to z ohms and C is equal to y into 1 plus y z by 4 Siemens. Now, we will talk about voltage regulation. Now, voltage regulation, what we mean by voltage regulation is basically when there is no load on the line, the voltage on the line will be somewhat higher. When we load the line, generally the loads will be of a lagging power factor loads. So, when we load these lines, then the voltage at the receiving end drops, and voltage regulation is basically telling us how much this voltage drop is in terms of the rated voltage or the sending end voltage. Therefore, we define this voltage regulation as a percentage voltage regulation. So, percent voltage regulation is defined as V r no load minus V r full load divided by V r full load into 100%. So, this is what we define. Basically, what we are trying to say here is that suppose we have a line which is loaded to its full load value, and if the load is suddenly thrown off, what will be the voltage at the receiving end? How much rise of voltage is there at the receiving end? So, this V r N L is showing what will be the voltage of the receiving end when the load is thrown off, and V r F L is the voltage when the load full load is there on the transmission line. So, this percentage voltage regulation gives us a very good parameter, because when we are designing a transmission line, we cannot allow more than about 8 to 10% voltage drop. So, voltage regulation will tell us what is going to be the voltage drop when the transmission line is fully loaded, because if the voltage drop is more, then we need some compensation. We will also, we had seen that when the load is capacitive in nature or of leading power factor, then the receiving end voltage can go higher than the sending end voltage, and this also needs to be checked for the transmission line, because if the receiving end voltage becomes very high, then it may endanger the transmission line insulators, because their design voltage will be based on the nominal value or the rated value for the transmission line. Therefore, if we see here for the short line, if when we want to calculate the voltage regulation, we need to calculate the voltage at the receiving end at no load, and as we have seen earlier, the voltage at the receiving end at no load for the short line is nothing but equal to V s, that is when IR is equal to 0, that is IR and IS both are equal to 0, because IR is, there is only IS and IR are equal. So, when the load current is 0, that is the system is at no load, then this drop is also equal to 0. So, VR is equal to Vs. For a medium length line, that is the pi model that we have used, we have seen that Vs is equal to A Vr plus Z into IR. Now, if we see this, then when the IR is 0, that is at no load, we have Vs is equal to A Vr plus Z into 0. So, Vs will be equal to A Vr only, and therefore, we have the no load voltage at the receiving end, that is Vr at no load will be equal to A into Vs, and therefore, we can calculate Vr at no load from this relationship. Now, we will take up the ABCD matrix for various kinds of line configurations, that is various kinds of network models or parameters that we use. So, if we have a simple series impedance, which is the case for a short line, then we have the ABCD parameters as A is equal to 1, B is equal to Z, C is equal to 0 and D is equal to 1. If we have a simple capacitance, this is what we many times use when we have to compensate for the reactive power drawn by the load. So, many times when the load, which is highly inductive, draws a large amount of reactive power, we need to compensate this reactive power by putting capacitance at the receiving end. The shunt capacitance at the receiving ends will then provide some reactive power, and this will compensate for the large amount of reactive power generated drawn by the load or consumed by the load. So, capacitance or the capacitor will generate reactive power at the receiving end itself and compensate for the large amount of reactive power drawn by the load. For simple shunt capacitance, the ABCD parameters will be A is equal to 1, B is equal to 0, C is y and D is equal to y. Similarly, instead of using a pi equivalent model, if we use a T equivalent model, where what we do is we divide the total series impedance into two equal parts and lump the total capacitance as one capacitance and put it at the center of the line. Then in this model we have Z by 2 and Z by 2 here and total y is here. In this kind of a model, which is a T equivalent circuit for the transmission line, the ABCD parameters will be given by A is equal to 1 plus y z 1, where this is z 1 and this is z 2. So, 1 plus y z 1 and B will be equal to z 1 plus z 2 plus y z 1 into z 2. So, and C will be equal to y and D will be equal to 1 plus y z 2. Again, for this, if you see, AD minus BC will be equal to 1. For the pi equivalent circuit, we have already seen. Now, here for this pi circuit, we have y 1 and y 2, which may not be equal, whereas for the nominal pi circuit we had both y 1 and y 2 were equal. That is, the total shunt capacitance was divided equally and placed, half of it was placed at the sending end and half was placed at the receiving end. Now, for this general pi circuit, if we calculate the ABCD parameters, we will get A is equal to y 1 plus y 2 z, B will be equal to z, C will be equal to y 1 plus y 2 plus y 1 y 2 into z, and D will be equal to 1 plus y 1 z. Again here if you see A D minus B C will be equal to 1. Now, as I said, many times we use compensation like adding a capacitance at the sending end, and then the line model will consist of two parts. One will be the transmission line model, another will be for the compensating equipment, and in that case we have two cascade ABCD systems, and for this complete system also we can find out the ABCD parameters, which will be nothing but this A B A 1 B 1 C 1 D 1 multiplied by A 2 B 2 C 2 D 2 will give the composite ABCD of this, that is A for the composite system or cascaded network will be A 1 A 2 plus B 1 C 2, B will be equal to A 1 B 2 plus B 1 D 2, C will be equal to C 1 A 2 plus D 1 C 2, and D will be equal to C 1 B 2 plus D 1 D 2. So, in this way we had seen how we can model the transmission line for short lengths and medium lengths. But when transmission line lengths are very long, which is the case in extra high voltage lines or some of the lines which are connecting the remote power generating sources such as hydel plants to the load center, then in that case it is no longer possible to use a lumped parameter model, and we will have to use the distributed parameter model or the more accurate model. Otherwise, the errors which will come because of using the lumped parameter model may not justify the simplification that we have used. So, here again we come back to the distributed parameter model. So, for long line, as I said, we will use this distributed parameter model. We have taken a section of line which is delta x in length, a small length delta x. The series impedance of the line is z into delta x, where z is the series impedance of the line, the resistance plus the inductive reactance of the line, r plus j omega l per unit length. So, that is represented here as z into delta x, and the total shunt admittance is y into delta x for this delta x part of the line, where small y is the shunt admittance of the line per unit length. As I said, for the transmission line at power frequency 50 hertz or 60 hertz, this part the conductance is negligible and this is generally neglected, and only capacitance is there. Now, we have taken the parameter x or the distance parameter from the receiving end side. So, the receiving end voltage or the voltage at a point at a distance x from the receiving end, we write this voltage as V at distance x, V x, and the current at this point as I at a distance x from the receiving end, that is I x. Similarly, the voltage of the line delta x meter in this positive direction, that is from receiving end towards the sending end, will be given by V into x plus delta x, that is voltage at x plus delta x from the receiving end. Current will be given by I at x plus delta x, that is current at x plus delta x distance from the receiving end. Now, with these values, now we will write the Kirchhoff's voltage law here we have V plus V at x plus delta x will be equal to V x, that is the voltage at distance x, plus the voltage drop, that is the voltage drop here will be I x into z delta x. So, the voltage at this end, that is at V at x plus delta x, is going to be equal to V at x plus the voltage drop, which is I at x into z delta x. That is what we have written here. V at x plus delta x is equal to V at x plus z into delta x into I x, I at x. Now, here as I said earlier, z is the series impedance per unit length, which will be r plus j omega l ohms per meter, and y is g plus j omega c Siemens per meter, where g for power frequency or transmission lines we have is almost 0 or negligible. Now, from this relationship of voltage at distance x plus delta x in terms of voltage at distance x, if we rearrange this, we will get as V at x plus delta x minus V at x divided by delta x. This delta x term we have taken on this side, and this V x we have taken on this side. So, this becomes negative, and this delta x comes in the denominator. So, V at x plus delta x minus V at x divided by delta x is equal to z into I at x. Now, if we take a limit with delta x tending to 0, then we can write this as dV x by dx is equal to z I x. That is, derivative of voltage at x will be equal to z into I at x. Similarly, writing the Kirchhoff's current law, we will have I at x plus delta x will be equal to I at x plus y into delta x into V at x plus delta x. That is, if we look at this, I at x plus delta x is going to be equal to I at x plus the current which is flowing in this admittance, which will be equal to y into delta x multiplied by voltage at this point, which is V at x plus delta x. That is why we have got I at x plus delta x is equal to I x, the current at x, plus y into delta x, the admittance, multiplied by V at x plus delta x. Again, rearranging by taking this I x on this side and dividing by delta x, we have I at x plus delta x minus I at x divided by delta x is equal to y into V at x plus delta x. Now, taking limit delta x tending to 0, we can write this as equal to d I x by dx, that is first derivative of current at x with respect to x is equal to y into V at x. Now, what we have is, if we see our previous equation for V, if we differentiate it again with respect to x, then what we will get is d 2 V x by dx 2 is equal to z d I x by dx. d 2 V x by dx 2 is equal to z d I x by dx. Now, substituting the value of d I x by dx from this point or this equation, we get this is equal to z into y into V x. We can write this as d 2 V x by dx 2 minus z y V x is equal to 0. That is, what we have done is taken this term on this side. So, d 2 V x by dx 2 minus z y V x is equal to 0. Now, this is a second order homogeneous equation, and we know the solution for this equation can be obtained in this form, where V x will be given by a 1 e to the power gamma x plus a 2 e to the power minus gamma x volts. So, this will be a general solution for this second order differential equation, where gamma is equal to root z y, and the unit for this will be per meter. Now, again differentiating this equation, we can write dVx by dx. Differentiating this equation with respect to x, we have got dVx by dx is equal to gamma a 1 e to the power gamma x minus gamma a 2 e to the power minus gamma x, and this will be equal to z into I x, because dVx by dx is z into I x. Therefore, we can write that I x is equal to this term divided by z. So, I x is equal to a 1 e to the power gamma x minus a 2 e to the power minus gamma x divided by z, and the gamma term which was here multiplied with a 1 and a 2, that we have taken in the denominator. So, this is z divided by gamma. Therefore, we can write I at x is equal to a 1 e to the power gamma x minus a 2 e to the power minus gamma x divided by z c. Now, this term z by gamma, we are writing this as z c. Z c is called the characteristic impedance of the transmission line. Now, if you see z c as we have put here is z by gamma, this is equal to z divided by gamma is square root of z y, and therefore, this is equal to square root of z by y, that is square root of series impedance by shunt admittance, and the unit for this is ohms, and therefore, this z c is termed as the characteristic impedance of a transmission line. Now, we need to find out the constants of integration, that is this a 1 and a 2. So, for this what we do is we use the boundary conditions. So, here using the boundary condition, that is at x is equal to 0, V x is equal to V r. So, at 0, V at 0 is equal to V r, and I at 0 is equal to I r. Therefore, V r will be equal to a 1 plus a 2, that is, if we substitute in this relationship x is equal to 0, then we get V 0 which is equal to V r is equal to a 1 plus a 2, as these terms will become 1. So, V r is equal to a 1 plus a 2, and again substituting it in this I x, here x is equal to 0, in these we will get I x is equal to a 1 minus a 2 by z c, a 1 minus I r is equal to a 1 minus a 2 by z c. From these two relationship, a 1 plus a 2 is equal to V r and a 1 minus a 2 by z c is equal to I r, we can calculate a 1 and a 2, and a 1 comes out to be equal to V r plus z c into I r by 2, and a 2 will come out to be equal to V r minus z c into I r by 2. Now, substituting the values of this a 1 and a 2 in the relationship for V x, we can get V x is equal to V r plus z c into I r by 2, that is a 1 into e to the power gamma x plus V r minus z c into I r by 2, this is a 2 into e to the power minus gamma x. And Similarly, putting it for the value of A 1 A 2 for I x relationship, we get I x is equal to V r plus Z c into I r by 2 into Z c e to the power gamma x minus V r minus Z c I r divided by 2 into Z c into e to the power minus gamma x. Now, if we again rearrange the equations for V x and I x, that is in terms of V r and I r, then combining all the terms of V r together and terms of I r together, then we can write from this equation, take all the terms which are having V r together and take all the terms which are having I r together, then we can write V x is equal to e to the power gamma x plus e to the power minus gamma x divided by 2 into V r plus Z c e to the power gamma x minus e to the power minus gamma x by 2 into I r, and I x will be equal to 1 by Z c into e to the power gamma x minus e to the power minus gamma x by 2 V r plus e to the power gamma x plus e to the power minus gamma x by 2 into I r. This is the relationship that we will get. Now, here we have got a relationship of V at a distance x in terms of receiving end voltage and current. Similarly, current at any distance x in terms of receiving end voltage and current. Now, from this we can, this term e to the power gamma x plus e to the power minus gamma x by 2 is equal to cos hyperbolic gamma x, and e to the power gamma x minus e to the power gamma x by 2 will be equal to sin hyperbolic gamma x. Therefore, we have this cos hyperbolic gamma x into V r V plus Z c into sin hyperbolic gamma x into I r. That is what we get here. That is, voltage at any point in the transmission line can be found in terms of the hyperbolic functions and the receiving end voltage and currents. Similarly, the current at any point in the transmission line, any distance x from the receiving end, can be found out similarly using the relationship I x is equal to 1 by Z c sin hyperbolic gamma x into V r plus cos hyperbolic gamma x into I r. Now, if you look at this, this is giving us a relationship of voltage and current at any point x in terms of receiving and voltage and current. Therefore, we can write this in terms of ABCD parameters as V x I x is equal to A x B x C x d x V r I r, where A B C D, A is equal to cos hyperbolic gamma x, B is equal to Z c sin hyperbolic gamma x, C is equal to 1 by Z c sin hyperbolic gamma x, and D is equal to cos hyperbolic gamma x. Again, you will see A d minus B c is equal to 1. Now, since most of the time we are interested only in the terminal conditions, that is conditions at the sending end and the receiving end, not anywhere in between the lines. So, we need to just substitute L instead of x, and then we will get the sending end voltage and sending end current. So, this relationship can also be put in the form of sending end and receiving end voltage and current, where x is replaced by L. That is, at sending end x is equal to L. Therefore, we can write this relationship as V s I s is equal to A B C D V r I r, and where A is equal to D is cos hyperbolic gamma L per unit, B is equal to Z c sin hyperbolic gamma L, and C is equal to 1 by Z c sin hyperbolic gamma L in Siemens. So, again we have got the ABCD parameters for the transmission line, and with for a long transmission line. The only thing here what we are saying is we have to use hyperbolic trigonometric functions, that is ABCD parameters are in terms of hyperbolic trigonometric functions, not just y and z as we had for lump parameter models. So, with this we stop today, and we will be continuing this long transmission line model in the next class, where we will talk about the velocity of propagation, the speed, the phase angles and other things. Also we will talk about regulation and efficiency of transmission lines. Thank you. Welcome to lesson 8 on power system analysis. This lesson is a continuation on transmission line modeling, especially modeling of the long line. Now, if you remember, in the previous lesson, that is lesson 7, we talked about distributed parameter model for long transmission lines, that is lines which are longer than 250 kilometers. For these lines, we said that the line voltage V x at a distance x from the receiving end is given by cos hyperbolic gamma x into V r plus Z c sin hyperbolic gamma x into I r, where gamma is called the propagation constant, x is the distance of the point from the receiving end. V r and I r are the voltages and currents at the receiving end. Similarly, the current at a distance x from the receiving end, I x, is equal to 1 by Z c sin hyperbolic gamma x into V r plus cos hyperbolic gamma x into I r, where Z c is the characteristic impedance of the transmission line, and it is given by square root of z by y, where z is the series impedance of the transmission line per unit length and y is the shunt admittance of the transmission line per unit length. As we see, these models, these equations involve hyperbolic functions. Now, since we have been writing all these transmission line equations in terms of ABCD parameters, we can write this equation also in those terms. So, in matrix form, we can use this as V x I x is equal to A x, B x, C x, D x and V r I r. This form, where this relationship is in terms of voltage and current at any distance x from the receiving end. Now, here if you see, A x is equal to d x and that is equal to cos hyperbolic gamma x in per unit. That is, if you see this relationship, this is your A x and this is your B x, this is C x and this is D x. So, A x is equal to D x is equal to cos hyperbolic gamma x, B x is equal to Z c sin hyperbolic gamma x, B x is equal to Z c sin hyperbolic gamma x, C x is equal to 1 by Z c sin hyperbolic gamma x and dx, as we have already seen, is equal to A x. So, this is the model where A and D are basically dimensionless, B has a dimension of impedance and C has the dimension of Siemens, that is admittance. Now, normally we are interested only in the terminal conditions, that is the sending end voltages and currents and the receiving end voltages and currents, rather than the voltage and current at any intermediate point on the transmission line. Therefore, we can find out the voltage and currents at the sending end in terms of voltage and current at the receiving end by substituting x is equal to L, where L is the total line length. This relationship, the voltage, that is the power flowing, is proportional to square of the voltage. So, if you are doubling the voltage, you are able to transmit 4 times the power, and so on. Now, I will show you the characteristics of this long lossless transmission line. When we have surge impedance loading, the voltage across the line all along from the sending end to receiving end is going to be same. If the line is unloaded, then the sending end voltage V s or V no load at any distance x, which we can write as a distance L, is equal to cos beta x or cos beta L for sending end voltage into V R and L. Now, in this case we find that the sending end voltage is going to be less than the receiving end voltage, and if we keep the sending end voltage as 1 per unit, then what we find that receiving end voltage is going to be much higher. Thank you, and in the next class we will take up some problems on transmission lines.